So we consider a rectangular metal plate. So it's a metal plate, okay? And on the xy plane, and the upper surface and the down surface are perfectly insulated. So the heat can only flow through the four sides of the rectangular metal plate. Okay. So the heat can only flow through the four sides. Okay. Okay. The heat equation can be described the evolution of the temperature U x y t of the metal plate at the point xy and at the time t. Okay. It's governed by a two-dimensional heat equation. Okay, so this heat equation here okay. So the square of the gradient denoted as the Laplacian operator. Okay, so this is the two-dimensional heat equation. Okay. In steady state, i.e. as t goes to infinity, u x y t, okay, u x y t remain unchanged with every graph in the B and time. So that come to 0. Okay. So when t goes to infinity, means in the steady state, the temperature will be dependent on t. All right. So then we have u of t equal to 0, infinity. Okay, that we will have a plus equation that equal to 0. Okay, so we have okay, now depending on the boundary condition, given on the boundary curve C. So the boundary curve C will be the convert of R. There are three different types of problem. Okay, so first, the first boundary value problem called the Differential problem. If U is prescribed on C, okay? So we call the Differential boundary condition. Okay, so we call a boundary condition to be a Differential boundary condition if the temperature U itself, okay, is prescribed on the boundary curve. This is called the first boundary problem, and sometimes it's called the Differential problem. Now the second boundary value problem, okay, BVP means boundary value problem. Boundary value problem. Okay. Just like we use IVP means initial value problem, right? So BVP means boundary value problem. The second boundary value problem is called the problem. Okay, if the normal derivative un, alright, so it's prescribed C. So the boundary condition is called the Newman boundary condition. Okay. The normal derivative means that at each point of the boundary, all right, we consider a vector, a direction normal to the curve at this point. Okay, so this is called n, right? And so we have the directional derivative. You know, for any function with more than one variable, okay, we usually consider directional derivatives. Okay, partial derivative is just special types of directional derivatives, right? Any questions about that? So do you still remember some of the facts for function of several variables in calculus? Okay. In general, if we have a curve like this one, right? So at this point, we find a normal vector. Okay. So that okay. So this is, we can define it is called the let's put this is n1 and 2, and so directional derivative x will be xu. Suppose this point is xy. Okay, and we want to know the directional derivative of u. Okay, in the direction of n. This is the x plus plus h and 1, y plus h and 2, okay, minus u x1 and h and take the limit as h equal to c. Okay, so this is the definition of directional derivative. Any questions about this definition? So I want to know that if the point is the point, right, change at x, y in this direction, the value, how the value of u changed. Okay, so it's called a directional derivative. Okay, and n is called normal because it is orthogonal to the tangent line. This is tangent line. Okay? Okay? To the curve. This is the curve, right? So this is the curve. So this is the curve here, right? And at this point, we have a tangent line. And so the normal vector is any vector orthogonal to the tangent. Right? So at every point, you have a normal vector, right? Normal vector. Actually, normal vector has two directions, either this way or this way, right? But for regions, normal code usually point to outward, okay? outward. So the normal will be in this way, outward. This is the convention. So normal vector always point to the outward. So here we have the normal vector. Okay, and we usually make the n such that the length is 1. So we usually use the so-called direction vector. And direction has length equal to 1. So it's a unit vector. Okay? So this is the convention we have used. Okay. So we specify the normal derivatives. Okay, on the boundary. Okay, and this kind of boundary condition is called the Newman boundary condition. Right? And it is called the second boundary problem or Newman problem. The third one, the third boundary problem, sometimes called the mixed. Okay? We repeat, or people call it Robin problem. If U is prescribed, okay, on a part of C, and the normal derivative UN on the raised part of C. Okay. And so people call this as the mixed boundary condition. So for example, you specify the temperature on this side and this side, but you specify the normal derivative on this side and this side. If you have such kind of boundary condition, you have the mixed boundary value problem, or the third kind of boundary value problem. Okay. So any questions? Right. Now we study a type derived PVP right prescribed as follows. Okay. So so let me give the Laplace equation as 12.6.7. Okay. So now I'll give U 0y equal to 0, U a y equal to 0, U x 0 equal to 0, and the U x b equal to f of x. Okay? So this is called 12.6.8 and A. Point okay. B 12.6.8 C 12.6.8 B. Okay, and for here y is in 0 to B. For here x is in 0 to A. Okay. So the initial condition is that we have specified that U is 0. U is 0. Right? So the temperature is 0 at these three sides. But for this side, the U is equal to f of x. Okay? So this side, U is equal to f of x. Okay, so this boundary condition is a differential boundary condition. Okay, according to our classification, right, of boundary problems. Any questions? All right. So we now proceed to solve. So we will use the method of separating variables. All right, so we'll use the method of separating variable to solve this derivative problem. Okay, so we'll let u xy to be equal to f of x and g of y. Okay. Okay, so first of all, we assume the solution is separable. Okay, so now 6.7 implies that we have, okay, which implies that so we have G, we have a prime of x and GY equal to minus f of x g to the power 1. Okay? So this is implies that 1 over f is square equal to minus 1 of g of 1 over g and we find that to be equal to minus k. Okay? Because this depends on depending what? Right? So we set it to be equal to minus k. Okay? So now we have two ordinary differential equations. Okay. And how about the boundary condition? For the boundary condition, we know in separable case that this is equal to F0 and the G1. Okay, this is equal to F(a) and G1. This is equal to f of x and the G0 here. Now, because f of x cannot be identical to 0, and g of y cannot be identical to 0 for y, so at least one of g1 is not 0, at least one of f of x not equal to 0. Otherwise, we will have trivial solution, right? So, to find non-trivial solution, f not equal to 0 and the g not identical to 0. Okay, so that the boundary condition imply that f0 equals 0, fa equals 0, and g0 equals 0. Okay? So immediately we know that f0 is 0, fa is 0, and g0 is 0. Right? So we have 3. How about GB? Well, okay, because the product is equal to f of x, so actually we do not know GB. We don't know. Alright, so GB is not known yet. But we have 3 boundary conditions. Okay? Right, so this is equal to 12, 6. Nine, 12, 6, 10, okay. 12, 6, 11, 8, 12, 6, 11, 3, 12, 6, 11, 3. Ah. So, the only non-trivial solution of 12.649 together with the ODE together with the 2 boundary conditions in 12.611 A to B. That for k equal to n times a squared. Okay, so we have the experience before. We actually this kind of OD appears again and again. So when k is equal to 1 pi x squared, then when kn, then we have f when x equal to sine 1 pi x divided by 8. Okay? For all n equal to 1, 2, 3, etc. Okay? So we know k can be and the f is equal to this one. Okay? So k can be this kind of numbers to have non-trivial solution. Okay? And for each such case of n, the corresponding solution is actually the sine function. Now, right? Now, now 12.6.10 implies that we have g minus n pi a square g. Right. So now we have this second order ODE, which is a general solution. Okay? Gy equal to gmy, which is an b n pi y divided by a plus bn b minus n pi y a. Okay? This is the general solution. Okay? Now, by 12.6.11.c, okay? Right? 0 equal to g0. So when y is 0, we have an plus bn. So this is implies that bn is equal to minus an. Okay? So we have bn equal to minus an. Alright, so the gn y is equal to 2an minus e a. Right. So this is the hyperbolic sign. Okay. Okay. So for each n, we have un x1 is equal to an star sine n pi x divided by a, and sine the hyperbolic sign, right, of n pi y a. Okay. To be solutions of 12.6 our So all these solutions are solutions of the Laplace equation together with three boundary conditions. Okay, so we have the last boundary condition to be satisfied. Okay. Now, so the crucial point is that since the Laplace equation and the three boundary conditions are in 12.6, 12.6.8, A to C are homogeneous and linear. Okay, so they are homogeneous and linear. U of x1. So any superposition of un x1. Okay, so so any superposition satisfy 12.6.7 and the same Laplace equation and the same boundary conditions. Okay, so any such superposition, right, satisfy Laplace equations as well as the same boundary conditions in 12.6.8 A to C. Okay, so no. All right. So now find the boundary condition in 12.6.8 D. Okay. We know f of x is equal to u of s. I forgot to mention. Please put. Forgot to mention that. Wait a minute. F 0 is 0 and f a is 2. Because the two edges, left and right edge, has 0 temperature. Okay? So please put the restriction. F0 is 0 and Fa is 0. Okay? Alright, so f of x is equal to this one, and so this is equal to summation star sine n pi x over a, and hyperbolic sine n pi ba. In pi b, because you have to put y equal to b here, so it's in pi b. All right, so this is become to an star hyperbolic sine n pi b over a, and the sine n pi x divided by a. Okay. So from this equation, we know which is the Fourier sine series extension of f of x. Okay, so this is the Fourier sine series extension of f of x. Right, so we know how to find the coefficient, right? So yes, Vn is equal to and pi divided by a, which is equal to 2 by a, equal to a, f of x sine n pi x divided by a. Right? So this is implied of a and star is equal to 2, okay, and the a sine n pi divided by a here. Okay, and okay. So finally, our solution would be 2a. I'm sorry. Hyperbolic sine. Okay, hyperbolic sine. Sorry. A sine n pi x a x sine n pi x divided by a, and then the box sine n pi y. Okay, so this is our final solution. So satisfying the original from the condition. In 12.6.8, A is B. Okay, so this is our final solution. Any questions? Of course, the same techniques can be extended to solve three-dimensional Laplace equations with the discrete boundary conditions. So what we'll see later on, okay, for later chapters of, for later sections of chapter 12, okay. And so we will give a short break, and after break, we will go back to chapter 11 to study Fourier integral, okay, because we will consider different problems with partial differential equations and the boundary conditions, especially with range, which is not a finite interval. All right, so let's take a short break now.